Hello, my name is Morgan Ewing, and today we are going to discuss plate and frame heat exchangers. Grant Foster will start us off with a brief discussion of the configuration of these heat exchangers, as well as a detailed animation of how they work. Abdul Ali will then present the different types of plate and frame heat exchangers and their industrial uses, followed by Sharmeen Muna, who will go over the heat transfer analysis associated with these heat exchangers. Keaton McCormick is presenting the advantages and limitations of plate and frame heat exchangers, and lastly, Brian Benoit will bring us to a close with an overview of plate and frame heat exchangers. We hope that this presentation is educational and highlights some key features associated with thermal fluid systems. Thank you and enjoy.
Good afternoon. Today I'm going to discuss the plate and frame heat exchanger construction and some of the key components that help to increase its heat transfer rates. The basic design components of the plate and frame heat exchanger are the two end plates, and between those two end plates are the corrugated plates where the heat transfer takes place. Those are typically made of titanium, plastic, or alloy. Titanium is preferred because of its anti-corrosive properties, although it can be expensive. The clamping bar is used to compress the corrugated plates between the two end plates, and there's a guide bar located on top to help for proper alignment. And on each corrugated plate are nitrile rubber gaskets which help direct flow. One of the key components of the plate and frame heat exchanger are the corrugated plates, and the purpose that they serve is to increase surface area. The corrugated plates also increase the stiffness, and most importantly, they create a turbulent flow, and that turbulent flow increases efficiency by breaking down the boundary layer that builds up on the surface, and it removes deposits from the heat exchanger surface. Another key component are nitrile rubber gaskets. They're made of nitrile because they have a high coefficient of elasticity, which means they can be heated and cooled without permanent deformation. They also have a high temperature capacity. The purpose of these gaskets is to direct flow in a counter flow direction between plates, and they're configured in 100-degree rotation every other plate. Quick animation will show the effects of those gaskets. The cool liquids will flow countercurrent to the hot liquids between every other plate, and the heat transfer occurs between each plate. Thank you very much.
Plate and frame heat exchangers are gaining in popularity faster than any other segment of the heat exchanger market. Part of the reason for the rising demand is that the plates can be added or removed depending on what is needed, expected, and given. In order to know the different industrial applications, let's first start by listing some of them. Brazed plate heat exchangers are exchangers used in many industrial and refrigeration applications. They're highly resistant to corrosion and very efficient and compact, making them an excellent economic choice. Plate fin heat exchanger use plates and fin chambers to transfer heat between fluids. They're often categorized as a compact heat exchanger to emphasize its relatively high heat transfer surface area to volume ratio. Moving to a plate frame heat exchanger, they use metal plates to transfer heat between two fluids, and their major advantage is that the fluid are exposed to much larger surface. Lastly, spiral plate heat exchanger are an exchanger made of two concentric channels on which spacer pins are welded to form the channel's gaps. Each channel gap and the width of the channel are selected to meet a specific requirement and working condition. All plate heat exchanger listed above has three major applications: liquid-to-liquid services, condensing and evaporative, and central cooling. Plate and frame heat exchanger are used for a number of HVAC applications. Their main duty within the system include heating, cooling, evaporating, and condensing. In chemical processing, plate heat exchanger can be used to recover organic compounds and cut costs. In oil and gas offshore operation, heat exchangers are needed to withstand corrosive media environments such as seawater, while also being lightweight and able to fit in small space. In food and beverage processing, plate heat exchanger plays a major role in pasteurization and other similar food-related processes. In marine, ship engines typically feature either an electric or a diesel hydraulic system in which a cooling system and gearbox lubrication, oil cooling are necessary. In conclusion, the compact size and the ability to add or remove plates based on needs make plate heat exchangers one of the most demanded in market.
Hello, I will be talking about the heat transfer analysis of a plate and frame heat exchanger. To begin with the analysis, we assume that the system is at steady state, it is adiabatic and end plates do not transfer heat, the heat exchanger is clean so there is no fouling, the flow is fully developed and is along a streamline. There is negligible resistance, it is incompressible, isothermal, and there is no phase change. The material properties remain constant, and the fluid properties are also constant and are taken at average of inlet and outlet temperatures. For maximum heat transfer, we also assume that it is at a counterflow. So why is counterflow better than parallel flow? As shown in this animation, in parallel flow, fluids flow in the same direction. So the temperature difference is large in the beginning, but it diminishes along the length until both fluids are at the same temperature, then no more heat can be transferred. Whereas in counterflow, fluids flow in opposite direction, so there is a lower inlet temperature difference. But as the two fluids travel through the heat exchanger in opposite direction, the fluid constantly passes new fluid which has a higher temperature gradient. This constant temperature difference along the entire length of the heat exchanger makes it much harder to reach the same temperature, and so more heat is transferred. Here we can see the sequence of equations needed for the heat transfer analysis. The fluid velocity can be calculated based on the given fluid properties. This is generalized as the formula will vary based on the number of plates. The Reynolds number for the hot side and the cold side can be calculated by this equation, and from the answer obtained, the corresponding friction factor and the Nusselt number can be determined. The Nusselt number is a flow-dependent one because if it is laminar, we use the modified Cedar-Tate equation, and for turbulent flow, we use the modified Diedrich-Wolter equation. Using values from fluid and material properties and the values obtained earlier, the convection coefficients for both fluids and the exchanger coefficient can be obtained. For the exchanger coefficient, the term T over K stands for the conduction coefficient. Additionally, the heat balance for both fluids and also for the exchanger can be calculated by the formula shown in this slide. Finally, the pressure drop for both fluids can be calculated by the given equation, where the first part shows the pressure drop in the plates and the second part shows the pressure drop in the port, which is basically accounting for minor loss.
I'm going to be talking about the advantages and limitations of the plate and frame heat exchanger. The advantages of the plate and frame heat exchanger include that it is easily maintained and simple to clean, and both of those are without having to take apart the configuration, and also it's more suitable for highly viscous materials. It's flexible, compact, and has close approach temperatures. The most important advantage of the plate and frame heat exchanger is it has a smaller fouling factor in comparison towards the other heat exchangers, and this is because it has high turbulence that's maintained in the flow, it has smooth plate surfaces, no stagnation points, and high convection coefficients. The limitations of the plate and frame heat exchanger include the leakage potential. Even though it is supposed to be firmly clamped together, it still has a greater leakage potential than the other heat exchangers. It also has a higher pressure drop, and this causes a higher cost for pumping than the other heat exchangers. And the limitation for pressure, it cannot be greater than 30 bar.
Overview of plate and frame heat exchangers. The plate and frame heat exchanger was invented in 1923 by Dr. Richard Seligman. Plate and frame heat exchangers are made of corrugated plates on a frame. Hot and cold fluids flow countercurrently within the exchanger. The hot fluid flows down one plate while the cold fluid flows up the other plate. Gasketed plate heat exchangers were the first type introduced and used high-quality elastomeric gaskets and design to seal plates together and protect against leaks. Recent advances have introduced brazed plate heat exchangers, which have a stainless steel composition with copper brazing, and welded plate exchangers, which have the plates welded together. Semi-welded exchangers feature a mixture of welded and gasketed plates. Plate and frame heat exchangers are incredibly common now. Larger, usually gasketed versions are used extensively in industry. Smaller, usually brazed versions are used in the hot water sections of millions of combination boilers and have made a great impact in domestic heating and hot water applications.